It's a real pleasure to be here. I'm actually not used to talking at this level. In fact, this book is my first attempt at a book for a general audience. I've written several textbooks before that are very technical, and no one ever asked me to come talk about them. So this is a little bit of a new experience. But let me just give you a little bit of background. I mean, part of the reason that I set out to write this book is that at Berkeley we've been under a lot of pressure because of major changes in computer science and a lot of pressure from the society around us. Huge numbers of students coming to take our classes, and a lot of interest in our subject, and also a lot of hype and a lot of fear about what's going on, because I think probably most of you who are here know that we're in the midst of some pretty big changes. We certainly see signs of it. I mean, you probably know about Vladimir Putin's speech to some million plus starting school children just last September, where he talked about artificial intelligence, and he said, whoever becomes leader in artificial intelligence will become the ruler of the world. And in a sort of similar vein, well, maybe not similar, a more dystopian vein, Elon Musk has been talking about how AI represents an existential threat to humanity, and he's calling for regulation. And one of the questions that I'm trying to address, I'm trying to get, in some ways with this book, a conversation going to improve our understanding of what's actually happening, because I feel like establishing regulations about things that you don't understand is usually not a very good idea. And so I think we need to develop this understanding and have the conversation before we can talk about regulations. So one of the questions that's driving the fear about AI, I think, is the question of whether artificial intelligence will exceed human intelligence. And I think this question is very difficult to answer, because we have to define human intelligence in order to answer it, and I think that's not an easy thing to do. So there's a much easier question that we can ask, however, which is, will machines exceed humans? And I think probably everyone in this room will know that the answer to that question is obviously yes. In fact, they already have. They have for many years. I think that what is scaring people these days is that the machines are now starting to exceed humans in dimensions that are a little bit unexpected, that are more about the cognitive functions of humans and less about the physical functions of humans and the precision with which we can do things. And so that's a natural change. But in terms of cognitive functions, I have a machine right here in my pocket that can remember far more phone numbers than I can, plus quite a lot more. It can find information much more easily. In fact, I have right here essentially a gateway to everything humans have ever published, which I can conjure up in this little box. And when I worked at Bell Labs in the early 80s, I learned a bit about the history in Bell Labs, and long before I was there in the 1950s, when they were starting to develop the direct dial phone system, they did all these human studies to try to ascertain how many numbers a person could keep in short-term memory. Turns out the answer is 7. And so that's why they established 7-digit phone numbers in the US. And of course that didn't scale very well, so they had to add area codes later on. But the hope was that you didn't have to remember the area code because they were going to be localized, and now that's kind of broken down, so nobody remembers numbers anymore. This device remembers them for us. So this device is actually kind of an extension of my personal human cognitive function, and it provides me with a service that really enhances my cognitive function. So really what I'm talking about in this book is trying to understand the part of this evolutionary process that we're going through right now, so that's the essence of the book. So I think the subtitle of the book is really fairly descriptive about what the basic theme is. It talks about the creative partnership of humans and technology, and this image, which I created, that's actually my hand. It's using the help of a little bit of software, again, enhancing my cognitive artistic capabilities. The software that I used was able to make it, render it to look like a drawing, right? But it wasn't actually me putting charcoal or pencil on paper. It was software enhancing my artistic skills. But the essence of this image is really, obviously this is drawn from an Escher, a very famous Escher drawing, which shows two human hands drawing each other. But in this case, it's very important that the other hand is a robotic hand, and it's really talking about a coevolutionary process between humans and technology, where in fact the humans are creating technology, but the technology is also in a very fundamental way creating the humans, in the sense that it has a really profound effect on our culture, and our mental capabilities and cognitive functions. Now, the title of the book is Plato and the Nerd, and the publisher hated this title. They tried to talk me out of it, and I brainstormed with them on quite a lot of alternative titles, and we never really came up with anything that worked. But the title is very indicative, and I'd like to just take a minute to explain it. It's trying to put into opposition two key ideas about how truth and knowledge come about. So the Platonic idea, represented by Plato, is that facts and truths about the world exist independent of humans in some Platonic heaven, and they're just waiting there for humans to discover them. And so the ultimate cognitive function that humans can do is to discover those truths that exist in the Platonic heaven. And if you think of artificial intelligence as one of those discovery processes, we're just trying to discover the processes of intelligence, then in some sense we abdicate responsibility for the results, because those truths already exist in that Platonic heaven, independent of us. And if we don't discover them today, our competing academics will discover them tomorrow, and therefore we're not responsible for the facts and truths that emerge at all. They exist independent of us. All we're doing is revealing them to humans. The opposing idea, represented by the nerd, is that facts and truths are actually created by humans, by our human cognitive function, and that in fact that process of creation can be quite quirky and idiosyncratic and can reflect the personalities of the individuals involved, and that you can create knowledge out of nothing. And if you buy that idea, then you absolutely cannot abdicate responsibility for the outcome of those ideas. And so the essence of this title is to try to put those two different views about knowledge head to head, and then start a conversation about which of those is involved to what degree in the development of technology. Now, a big part of that tension is a tension also between science and engineering, because I was brought up with a very strongly scientific education, and the Platonic view, I think, was really driven into me, where valuing discovery was really what it was all about. And the engineering side, which is the more represented by the nerd, is about creating things that never before existed in any Platonic heaven or anywhere else. So the book confronts this question about, what is the relationship really between science and engineering? And the book talks quite a bit about this LIGO project, the Laser Interferometry Gravitational Observatory. And I didn't know when the book was finished that these guys would get the Nobel Prize for this book. Rainer Weiss at MIT and two of his colleagues at Caltech just got the Nobel Prize a couple of months ago. And I want to read you the citation for the Nobel Prize. It says it's for decisive contributions to the LIGO detector and the observation of gravitational waves. And one of the interesting things about that citation is that it doesn't mention discovery. And in fact, if you think about it, the LIGO detector is really a magnificent piece of engineering. It is an extremely sensitive instrument that can measure changes in distance over a 4-kilometer range of a small fraction of the diameter of a proton. It's a beautiful, beautiful piece of engineering. And I believe that actually this might be the first Nobel Prize citation that actually overtly acknowledges that. It's for decisive contributions to the LIGO detector, an engineered artifact rather than a discovery. Now, if I were to ask most of you in the room, most of you in the room would, if I ask you when was the transistor discovered, you would say, well, it was discovered in the late 1940s at Bell Labs by these guys, Brattain, and Shockley, and they actually got the Nobel Prize in 1956, and their citation read, for the discovery of the transistor effect. Now, as far as I know, the transistor effect has never been found in nature. So they seem to have discovered something that didn't exist. But interestingly, if you dig into the history, this fellow, Julius Lilienfeld, who everyone has forgotten, was issued a patent in 1930 for the field effect transistor. He didn't call it that, but it is a field effect transistor. You can dig out the patent, you can look at it, it's a field effect transistor. He first invented it in 1925. But you don't get a Nobel Prize for inventions, and you don't get a patent for discoveries. So the transistor was actually invented 20 years before it was discovered. That's a little bit curious, okay? So there's an interesting relationship here between science and engineering that I think is a bit subtle and isn't immediately obvious. So one of the epiphanies that I got in working on this book was this observation that scientists and engineers both use models intensively. It's all about models. In science, the value of a model lies in how well it describes a physical system. This is what scientists do. They create models to describe the physical system, and the model is good if it describes that physical system well. But in engineering, the value of a physical system lies in how well its behavior matches that of a model. If I give you a piece of silicon that doesn't realize this logic diagram of my circuit, then that piece of silicon is junk. Okay? These are very complementary uses of models, and most people who use models, both in science and engineering, don't really realize which of the ways they're using models. But these are two very different uses of models. So put another way, a scientist asks, can I make a model for this thing? An engineer asks, can I make a thing for this model? Another manifestation of this contrast is that a scientist tries to shrink the number of relevant models, the ones that are needed to explain the physical world. An engineer tries to grow the number of relevant models, the models for which we can build physical systems. These are very different uses, and they're very complementary. Now, my book then goes into the question of whether engineering and science are rational, systematic, and logical. And here I'm going to quote Donald Rumsfeld, which I don't do very often. I think most of you know that he was Department of Defense Secretary during the Iraq War, and he talked about, well, there are the known unknowns, the known knowns, the known unknowns, and the unknown unknowns. I'm a digital guy, and so my immediate observation is that there's a missing fourth category, which is the unknown knowns, right? These are the things you know, but you don't know you know them, okay? These form an enormous part of most of our intellectual activity. And I think the person who best articulated that was another Berkeley professor, Thomas Kuhn, who used the word paradigm in the context of sciences for these unknown knowns. They're part of the backdrop of your thinking, but you're really largely unaware that they're even there, and you're certainly unaware of how much they're shaping your thinking. This happens in technology extremely strongly. A lot of what we think of as very objective aspects of technology are not actually objective at all. They're the results of human creativity. If you think about the design of a chip, you can start with extremely tiny transistors. This is a picture of a transistor that was made one floor down from my office in Corey Hall in Berkeley in our microlab in 2001. It's a FinFET transistor with a 20 nanometer gate width, okay? Extremely small transistor. The transistors that are made on the fabs at Intel these days are about the same dimension, okay? Many years later, this has gotten commercialized. But there's many layers of abstraction between that transistor and that chip. So this die image shows an Intel Haswell chip that has 1.4 billion transistors in an area that is smaller than 2 centimeters squared. And those 1.4 billion transistors can switch 2 billion times per second. So the dynamic range between the single transistor, the single switch, and that hugely complex chip is so big that human human designers would not be able to grapple with this complexity of design without many layers of abstraction between the switching transistor and that larger system. And so my claim is that each of those layers of abstraction is actually a human creative artifact, and many times it reflects the quirkiness of the humans. And this is particularly viewed when you elevate this to the software level, where you start to see real personalities emerging, okay? Very idiosyncratic stuff that can take the form of programming languages, for example. And many of these are languages that are extremely widely used, and if you can almost do a anthropology of languages, studying how in fact they came to be the way they came to be. So my book emphasizes in part this sort of quirky creative process that is really not the sort of objective, dispassionate thing that many people think engineering is. And I also talk about this idea that technology is actually co-evolving with humans in a very Darwinian way. And that observation I actually first got from George Dyson's book. So George Dyson is the son of Freeman Dyson, who's a famous physicist. George is not quite as famous, but he wrote this really wonderful book called Turing's Cathedral, where he talks about this coevolutionary process between software technologies and humans. And one of the quotes from his book is he talks about, the big computer, talking about actually these Google server farms, is doing everything in its power to make life as comfortable for its human symbionts. The humans are taking care of developing that software, and the software is taking care of the humans to enable them to further develop the software, okay? So that idea of a symbiosis is what ultimately inspired this cover image, of course. And just to try to entice you to read my book, here's a little quote from it, where it asks a question about artificial intelligence specifically. Are we playing God, creating a new life form in our image? Or are we being played by a Darwinian evolution of a symbiotic new species? Are humans the purveyor of the noisy channel of mutation, facilitating sex between software beings by recombining and mutating programs into new ones? This is what most programmers do, is they take a bit of code from here, a bit of code from there, and they glue it together, and they make a new bit of code, okay? Most of the code that they create then goes and dies, but some of it procreates and mutates into other code, okay? Very Darwinian kind of process that's happening there. Now, my book has kind of a yin and yang part to it, and I don't want to spend too much time here, but again, just to entice you, there's a whole section, the second half of the book is more about what computers can't do than about what they can do, and here's a few of the characters that appear in that part of the book, ranging from Pierre-Simon Laplace, the physicist John Archibald Wheeler, the Reverend Thomas Bayes, Alan Turing, of course, and Claude Shannon. So closing, about artificial intelligence, are we trying to replicate human intelligence? Do we want, in fact, computers replicating human intelligence? I personally do not want to have to argue with my car about getting to school on time. It's hard enough to have that argument with my daughter. I think that it's not even desirable, whether it's achievable or not, right? And moreover, I don't believe it's what's happening. We're actually not creating human-like intelligence. We're creating intelligences that are really quite different from human intelligence. I also talk about this observation in the book. I saw this accident, and my immediate reaction was that car should be ashamed of itself. It was a relatively new car. There is no excuse for putting cars on the road that will do that, okay? There really is no excuse today. And yet we're still doing it. And the reason that we're doing it is for cultural reasons. The car manufacturers, I asked people at Ford, executives at Ford, why do they do this? I mean, this car was actually equipped with a adaptive cruise control system, so it had all the hardware to apply the brakes before colliding into the system in front, but the adaptive cruise control system wasn't turned on. And, the executives at Ford say, well, the liability laws and all this, there's all these cultural issues, right? And so this culture is very tightly intertwined with the technology, and it really can't be separated from the technology. Culture and technology are evolving together, and we need to understand that process better. Thank you very much.